following up on the video that I made previously regarding aperture and velocity of flow, I want to talk a little bit more about this system. There's a couple of things to notice about the design of this system that helps us to isolate aperture diameter only, or size, and its effect on the velocity of flow. First of all, the velocity, or the aperture that we are considering, is very small relative to the size of the enclosure, the size of the boundary enclosure on each side. So even though we vary the size of the aperture between very small and a little bit larger, even relatively larger, in this case, our apertures of consideration are small relative to the area of the boundary that is enclosing the pressure. That ensures that the pressure can remain constant just on each side of the boundary. Another thing to notice about this system is the boundary where the aperture exists is very thin. That ensures that the flow through the aperture is very uniform and laminar. Now that's important to reduce viscous effects. I'll talk a little bit more about that later on. But if we make one change to this system, where we will then add width to the boundary, things change a little bit. So considering that we're going to make a thicker boundary, now if we have a small aperture here, is the velocity the same as it was before? Well, the answer is positively no, because any fluid with viscosity, and that includes air, the length and the diameter contribute to the viscosity losses in this system. So by lengthening the aperture to the point where it is now longer than it is wide, we have a much more resistive path, and the velocity will be now slower. Even though the diameter of that aperture is the same, the length, it has length to it now. So the flow velocity is less, and the flow, the volumetric flow, is also less. And this applies to airflow, as brass musicians are interested, and they rarely consider this when they're considering how a smaller aperture or a narrowing oral space will affect airflow. Now, many of you have made comments to me about, well, what about my garden hose? The velocity is always higher when the nozzle is smaller, and it's low. The velocity is much, much lower when there's no nozzle present. It's just a hose with no nozzle. Well, if you consider that entire system, you can't base your judgment on all apertures by a complex system with various things in play. So in that regard, since you want to change the subject to water, we'll do that. First of all, let's ensure that we have constant pressure. So what we're going to have is a vessel with water standing in it at some depth. I'm also consider that the size of this vessel is practically infinite, such that the water level does not change as we flow a small amount of water out of it. Now the pressure varies in a water container with depth. Anyone who dives, scuba divers and swimmers, should know this firsthand. So at some height above the base or below the surface, there is a pressure. So there's a constant pressure at any of these levels. Pressure increases as you go deeper into the tank or into the water vessel. But let's put an aperture then at some known depth. So since the pressure is constant at this point, there will be a velocity of flow out due to the pressure difference between the water pressure at that point and the atmospheric pressure here. Now the atmospheric pressure is relatively constant for limited heights. We know that in practice it does change with very large changes in elevation, but not near as quickly as a fluid tank. If there were an aperture here, a water aperture, there would be a velocity of flow out. What you would get from these is this one would travel faster at this point than this one. Because of the pressure difference related to the velocity through the aperture, just as I talked about before. Now, since we can assure a constant pressure here of the water right before this, what if we attach a long narrow hose? Will the velocity coming out of the hose now be the same as it was when we had just the same diameter opening at the boundary of the vessel? The answer is no. The reason is the pipe that we added here, or the hose, added viscous effects due to flow. Now, if I were to have a hose with a very small aperture, what would the velocity of the small diameter of water coming out of that be? Well, it would be very, very nearly the same as if that same aperture were at the supply pressure. And the reason is, if the width of the supply hose is sufficiently wide enough, There's limited, very limited flow if you limit the flow with a very small, or if there were zero flow. If you were to block flow and have a pipe joined to a tank of some length, the pressure here is exactly the same as the pressure here. Now, if I open an aperture very, very small, the velocity is the same as if that aperture were at the tank. Practically the same. But as you open the aperture, remember, flow is going to be equal to the velocity of the flow out of the aperture times the area. So considering you have this a fixed velocity, if I double the area, I double the flow. Well, let's make that a little bit wider. What happens now? The flow is greater. Let's remove it all. Let's remove it completely and have simply the pipe opening. What's the velocity now? It's much less. And the reason is because we now have, as I described before, we now have an aperture, basically, or a flow path that is very narrow relative to its length. And if that becomes sufficiently narrow, not only do you have laminar flow that is viscous, you can have turbulent flow, and you can lose your pressure very quickly as you move down the pipe. So the pressure here does not change. I'm talking about the total pressure. Total pressure here is going to be much, much less than the pressure of the vessel. So when you ask me, what about the hose pipe? This is the scenario. If I add a flow restricting nozzle that will preserve the pressure almost nearly to what it is from the supply, and you'll have the same velocity as if that aperture was at the pressure supply. But regardless of this case, the velocity through any aperture is proportional to the difference in pressure on each side of the aperture. For higher flows through the pipe, for larger apertures, the pressure begins to drop. So while you might have a pressure here at the beginning of the pipe, the pressure drops by this amount. It'd be the same pressure, or less pressure. It might be the pressure that's here in the tank, or here. Or for very, very long hoses, and long and narrow hoses, you would be lucky to have pressure at the end of the hose that is just below the water line. And that's what's happening with our hose pipes. The nozzle is not doing some magic increase in the pressure supply. It just preserves whatever supply pressure you have by severely limiting the flow. But I want to get into other subjects in the future and how they do apply to brass playing. We've gone off on a tangent because you can't discuss apertures and trumpet playing and tongue arches and airways without someone trying to compare it to a garden hose and say that there is some advantage to a tongue arch and narrowing the air path before the aperture because of that violent flow that comes out of their hose nozzle in their garden. It does not apply. It's a different scenario. So I'll get to some other subjects as we move forward. This is a long video, and if you stayed with me till now, you don't have much better to do. But if you're a brass player that's interested and you're interested in this sort of thing, you can learn from it and use it to your advantage. Thanks for watching.